Hello everyone, I'm Devan Dash and I'm a PhD student at the Spark Lab, Purdue University. Today I'll present my work on current domain signature attenuation hardware to protect against deep learning side channel attacks. This work is in collaboration with Georgia Tech and Intel Labs. Computationally secure cryptographic algorithms, when implemented on a physical platform, leak critical information in the form of power consumption, electromagnetic radiation, timing, cache hits and misses, and so on, leading to side channel attacks. In this work, we will focus on power consumption based side channel attacks. Here is the outline of today's presentation. First, we will begin with the background of deep learning side channel analysis. Next, we will discuss the attacks on our unprotected AES 256. Then, we will study the state-of-the-art countermeasures and move on to the design of our implementation. Finally, we will analyze the efficacy of the proposed countermeasure and conclude the presentation. This slide shows the different types of side channel analysis attacks. In the case of non-profiled side channel analysis, a direct attack is performed on the target device by correlating the actual trace with a Hamming weight or a Hamming distance leakage model. And the attack requires thousands of traces against an efficient hardware implementation. On the other hand, profiling attacks are performed in two phases: the training phase, which is also known as profiling, and the attack phase. Deep learning side channel analysis is a type of profiling attack in which a deep neural network is trained using multiple traces. The entire heavy lifting is thus offloaded to the training phase, which happens offline prior to the actual attack. During the attack phase, unseen traces are fed to the trained deep neural network, which then predicts the correct key byte. The attack succeeds with as low as a single trace, which increases the threat surface for embedded devices significantly. Compared to the statistical template-based profiling attacks, deep learning frameworks are more automated and would aid an attacker mount successful attacks on crypto implementations without prior knowledge of the architecture. Here we see the deep learning based power side channel attack setup. During the profiling phase, traces are collected by varying the subkeys, and a 256 class DNN model is built for each key byte. During the attack, a few traces are required to extract the correct key byte. Other than the 256 class identity model, we can also train a 9 class deep neural network using Hamming weight or Hamming distance model, which requires more number of traces to attack. However, we use the 256 class model to reduce the attack time. The figure on the right shows the attack accuracy of each of the individual classes for a 256 class DNN. The black curve shows the accuracy of each individual key byte. Now, for the mispredictions by the DNN, the red curve shows the maximum percentage to which the neural network predicts to a particular class that is incorrect. Hence, training a 256 class classifier uniformly is challenging and requires the proper choices of network architecture and the hyperparameters. Here we see the evolution of deep learning based side channel attacks. In 2011, Hospodar et al. For the first time used support vector machines to attack an unprotected AES implementation. In 2013, Lohmann et al. Used support vector machines and random forest based models to break masked AES implementation of the DPA contest V4. In 2016, McGravy et al. Showed for the first time deep learning based attack on the masked AES. Following this, in 2017, Kagli et al. Demonstrated breaking clock misalignment based countermeasures using convolutional neural networks. Recently, at the DAC 2019, we showed the first single trace cross device portable deep learning based side channel attacks. This slide shows the feasibility of a single trace attack when the DNN is trained to achieve 99% accuracy. Hence, as we can see, the time to attack is drastically reduced compared to the non-profile attacks. Now, to evaluate the countermeasure, we introduce two metrics of entropy for deep learning side channel analysis, which are measures of the efficacy of the countermeasure. The measure of entropy for training depends on the ratio of the number of traces required to train the DNN for the protected and unprotected implementations respectively multiplied by the ratio of the training accuracies achieved. Similarly, the measure of entropy for testing is the ratio of the number of traces required to test the DNN for the protected and unprotected implementations respectively multiplied by the ratio of the test accuracies achieved. Let us now look into the attack on our unprotected AES 256 implementation. Here is the deep neural network architecture with three fully connected hidden layers. The ReLU nonlinear activation function along with dropout and L2 regularization to prevent overfitting. The input layer corresponds to the number of time samples in each measured power trace. The output layer has 256 classes, which corresponds to the 256 different possibilities of the first key byte under attack. The effect of hyperparameters, the number of hidden layers and the number of hidden neurons per layer is shown here. We see that as the number of hidden layers is increased beyond 3, the DNN starts overfitting to the training data and hence the test accuracy reduces. Also, 1000 hidden neurons in each layer is the most optimal choice. The figure on the left shows that the deep neural network overfits for the learning rate more than 10 to the power minus 3. The figure on the right shows that the training and validation accuracy reaches 99.9% within 10 epochs with 5000 training traces. The test accuracy of the DNN reaches 99.9%, and the confusion plot on the right shows that the DNN is able to predict the key byte correctly and a single trace attack can be performed. Now, let us look into the state-of-the-art countermeasures. The existing logic level and architectural countermeasures include gate level masking and introducing clock randomizations. The timing-based countermeasures like clock jitter or trace misalignment have been broken using convolutional neural networks. The gate-level masking countermeasures have been also defeated using deep neural networks. The physical circuit-level techniques include switch capacitor current equalizers, integrated buck regulators, and digital LDO. The proposed current domain signature is the first physical countermeasure which evaluates against the profiling-based deep learning side channel attacks. The switch capacitor current equalizer based implementation operates in three phases. In the first phase, the load capacitor is charged to the supply voltage. During the second phase, the crypto operation is performed, and finally, in phase 3, the output node is discharged to a fixed voltage to clear the residue. This technique offers high security but suffers from multiple trade-offs between performance, area, power, and security, leading to a 2x performance degradation. Recently, integrated voltage regulators involving buck converters and series LDOs have been proposed. However, they suffer from large passives leading to area overheads. Also, an ideal series LDO based implementation inherently leaks critical information. Let us now move on to the design of the countermeasure. The underlying key concept behind the proposed countermeasure is the signature attenuation. On the left, the supply current contains the correlated current signature from the unprotected crypto engine. Imagine if we can somehow embed the crypto core within a signature attenuation hardware such that the crypto current is suppressed significantly before it reaches the supply pin, then the minimum traces to disclosure or MTD is proportional to the square of the attenuation factor, which means that if we can provide a signature attenuation of 100x, the MTD would improve by a factor of 100 square. This technique of signature suppression in the current domain provides orders of magnitude improvement in the security of side channel attacks. Now, ideally for maximum protection, we need infinite attenuation, which means that the supply current should be independent of the crypto current. Well, the first thing that comes to our mind is a constant current source. However, a constant current source cannot drive a variable current load. Hence, we need a capacitor to account for the differences in the current. Now, to handle the PVT variations, a switched mode controller with guard band is used. The SMC loop is a low bandwidth digital loop which senses the voltage VDIG and sets it within the guard band VTarget plus delta plus and VTarget minus delta minus by turning on or off the required number of current source slices. Now the current from the top is set to a quantization level closest to the average crypto current. The quantization error in the current is passed through a bypass path, which is the bleed. It provides a local negative feedback and also allows low frequency regulation. In steady state, as the VDIG node remains within the guard band and the current from the top is equal to the average current, the switch mode controller remains disengaged and the attenuation is given by the output impedance of the current source as well as the load capacitance. Now, to reduce the area overheads, we need to minimize the capacitance and maximize the output impedance of the current source. Hence, we use a cascade current source which provides a very high output impedance and allows a 10x lower load capacitance. So, we choose to tolerate the 30 to 50 millivolts fluctuation at the VDIG node across the load capacitor, and the high output impedance of the current source ensures that the signature is not reflected to the supply current. Here we see the operation of the switch mode control loop. Whenever the voltage Vditch is more than Vtarget plus delta plus for a number of SMC clock cycles, one CS slice is turned on. Similarly, when the voltage Vditch is less than Vtarget minus delta minus continuously for a number of SMC clock cycles, a current source slice is turned off. The figure on the right shows how the SMC loop turns off the required number of current source slices. Once the steady state is reached, that is when Vditch remains within the guard band, the SMC remains disengaged. Here we see the design space exploration of the current domain signature attenuation hardware. The figure on the left reveals that a bleed size of 400 and a dropout voltage of 300 millivolts across the current source is the most optimal choice. Higher bleed size would increase the current drawn from the supply and reduce attenuation. Figure on the right shows that a bleed bias of 350 millivolts is optimum, beyond which the bleed goes towards cutoff and the attenuation reduces. Here is the full system architecture of the protected CDSA-AES. Highly isolating switches for Vditch observability is designed, and the switch remains off during the normal operations. Let us now look into the efficacy of the countermeasure circuit. This slide shows the test chip and the design details of the system. The unprotected AES-256 is powered at 0.8 volts at 50 MHz. It is a high-performance parallel data path implementation and requires 14 cycles per encryption. Time domain measurement results clearly shows the 14 rounds of encryption for the unprotected AES trace in red, while it remains below the noise floor at the supply node for the CDSA-AES, showing an attenuation of greater than 350x. The figure on the right shows the Vditch node where we can still observe the 14 rounds, but it is an intermediate node of the circuit and hence is inaccessible to an attacker. Note that, as mentioned previously, the high output impedance of the current source on the top ensures that the correlated signature is significantly suppressed at the supply pin. Here we observe the effect of the current domain signature attenuation on the deep learning side channel attack training phase. Even after 10 million traces are fed to the deep neural network, it does not learn the leakage patterns, and the validation accuracy remains close to a random choice, which is 1/256 or 0.3%. The figure on the left shows the confusion matrix for the unprotected AES-256, where we see that more than 99% of the test traces are classified correctly. The figure on the right shows the confusion matrix for the protected AES implementation, where we see the DNN is not able to classify new test traces and the test accuracy is just as good as random. This slide shows the comparison of the CDSA-AES with the state-of-the-art circuit level countermeasures. This is the first work showing the efficacy against deep learning based side channel attacks. The DNN does not learn the leakage information from the measured protected traces even after 10 million measurements, which provides an improvement of 2000x over the unprotected implementation. Also, this technique has comparable area or power overheads compared to the prior works. Moreover, it does not have any performance degradation. We will now move on to the conclusion. Here is the summary of the deep learning side channel attack performance on the unprotected and protected AES 256. The DNN for the unprotected AES could be trained with only 5000 measured power traces, and the single trace DLSCA attack was successful with an accuracy of 99.9%. On the other hand, for the protected implementation, the DNN could not be trained even with 10 million measured traces, and the test accuracy was as good as random, which is 1 over 256 or 0.3%. Hence, from the definition of training entropy, it is in the order of 10 to the power 5, while the test entropy evaluates to infinity, since the model could not be trained for the protected implementation. To conclude, this is the first physical countermeasure evaluated against the deep learning based side channel attacks. The DNN could not be trained even with 10 million traces for the protected implementation, showing an improvement of 2000x over the unprotected implementation. It incurs a power overhead of 49% and an area overhead of 36%, which is comparable to the previous countermeasures. It is a generic countermeasure and can be extended to any other crypto algorithm as a wrapper around it without any performance degradation. Thank you.